In this video, we're going to take a look at amides. So amides are organic compounds, and what they have is a carbonyl group for a functional group that's bonded to a nitrogen. So we have carbonyl over here, and then directly next to it, there's a nitrogen group, and that could have either H's on it or carbon chains on it, much like amines, but the main difference is the carbon next to the nitrogen group is a carbonyl group. So there's that double bond on that carbon, and then there's more carbons along the other end if you want. You can have more carbon chains there. So just like with amines, you can have primary, secondary, or tertiary amides. So a primary amide is one where you only have the one sort of carbon chain connected to that nitrogen with the double bond O, and there's no other carbon chains on the nitrogen. It's just H's. Whereas a secondary amide has two carbon chains, one being the one with the double bond O in it. And then the tertiary amide has three carbon chains, one being the other one being the one with the double bond O in it. Similar to esters, amides are made by combining two different organic families together. You'll actually combine the carboxylic acid with the amine. And so when a carboxylic acid reacts with an amine, it'll make an amide and then release water as well in a condensation reaction. So it's called an amide synthesis. And you can see that in this reaction here, we have the carboxylic acid right here reacting with the amine. The OH and the H are removed, and you connect the C to the N there, and you get your amide over here, and your water is released. And that bond that forms where you have now linked the carboxylic acid to the amine to make the amide. That's called an amide bond. So an amide bond over here. And it's actually a bond in proteins. So if you have studied biology and you've seen biological molecules like proteins, proteins consist of amino acids being connected together. And essentially when an amino acid is connected to another amino acid, you have that condensation reaction occur where the carboxylic acid end, carboxyl end of an amino acid reacts with the amino end of amino acid in much the same fashion that we saw over here. And the resulting connection is the amide bond that has formed. And it's also called your peptide bond. So that's a biological application of the amides. So how do we name amides? You can take a look at a variety of different examples here and try to figure out the naming rules for yourself. But if we take a look here, we have a 3-carbon amide, and so we call that propanamide. So as you can see, we named the longest parent chain that contains the amide group, including that carbon, which is part of the parent chain, and just replace its ending with amide. Over here, you can see a similar example. So propanamide again, but this time the nitrogen has some substituents on it. So we have NN dimethyl propanamide. Let's go take a look at another example over here. Here we have, once again, a 3-carbon chain, so it is propanamide. We have substituents on our N, and we also have substituents on our carbon chain. So you'll see we have N-ethyl, and then we have N, and then 2-methyl, dimethyl, since there's 2 of them, propanamide. Typically for amides, what we do is we list the substituents on the N first, and then we list the substituents on the carbons second. So, and then we follow alphabetical order within that naming rule as well. So let's go ahead and do some examples together where we will name some amides or draw them. So here we have a carbon chain on our amide, which is 1, 2, 3, 4 carbons long. So that's a butane chain. There's no substituents anywhere, so it's simply butanamide. And of course, carbon number 1 would be where your amide group is right here. So we're not really going to have to list where the amide is because it's typically going to be on carbon number 1. N-methyl butanamide. So let's go ahead and draw that out as a bond line diagram. So butanamide. So 1, 2, 3, 4. This will be our double bond O here. This will be our N over here. We'll have a methyl connected to it, and don't forget you'll have to have at least one H. You can draw the H just connected to it directly, just condensed, or with a line. I just did it with a line here, but you could have done this. Like that. Remember, this indicates that the line is attached to the N, not the H, because then H would have two bonds otherwise. Okay, let's take a look here. Here we have our longest chain that contains the amide group. It's over here. So that's a 1, 2, 3, 4. So it's a butanamide again, but this time we have some substituents on the N. We have a methyl and we have a 1, 2, 3, 4. So we have an N-butyl, N-methyl, and then 1, 2, 3, 4, butanamide. All right, over here, we have an N-ethyl 2,4,5 trimethyl decanoamide. That's a 10 carbon amide. So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our double bond O would be here. And then that's connected to an N. And on that N, there's an ethyl. So there must be an H for the remaining part. So here's our ethyl, H for the remaining part there. Now on carbon 2, 4, and 5, we have methyls. So this is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We start on this side because carbon number 1 is the one that has the carbonyl group on it, or the, in this case, the amide group. So carbon number 2, we have a methyl. Carbon number 4, we have methyl. And carbon number 5, we have a methyl. Just like that. All right. Let's go ahead and try this one here. So you can try to pause the video and try it yourself. So here we have our amide group. This is the longest chain with the amide there. We have 1, 2, 3, 4. So it's a butanamide. But notice we have some substituents. We have an ethyl group over here and a methyl group over here. So we're going to have an N-ethyl and then a 1, 2, 3, 4, 3 methyl, and then we have 4, so butanamide. Like that. Okay, next we have NN diethyl 2-hydroxy 3-methyl butanamide. So let's go ahead and draw our 4-carbon chain. 1, 2, 3, 4. Double bond over here. This is our N. On our N, we have ethyls. This should be diethyl. So we have an ethyl here, so 1, 2, and an ethyl here, 1, 2. No H because we have 3 things connected to our N so far. We have a 2-hydroxy. So remember, hydroxy means OH when it's a lower substituent. So it's carbon number 1, 2, 3, 4. So we have OH over here, and then 3-methyl right there. This is a benzene with a amide group connected to it. Just like we had benzamine, we have benzamide. Like that. So now that we know what benzamide is, we can do this example over here. 5-fluoro 2-hydroxy N-isobenzamide. So let's go ahead and try that out. We'll draw out our benzene ring. It's a benzamide, so We'll have our double bond O here, our NH2 here, but it wouldn't be NH2 because we have a substituent on the end. It's an isopropyl. So it's like this, and then it's connected to the second C of that propyl group. And on carbon number 2, so this is carbon number 1, carbon number 2 will have OH, and then 3, 4, 5 will have our fluoro, and then this is 6, nothing there. So we have our 5-fluoro, 2-hydroxy, N-isopropyl benzamide. And that there represents some examples of drawing and naming amides. So some properties of amides that you do need to know are that they're weak bases. So they're bases. We'll understand what weak means later on, but they are bases. So they'll react with acids. Generally, they're fairly insoluble in water. Small, because they do have a lot of, they're basically big carbon chains. Smaller ones are slightly soluble in water because the NH can hydrogen bond. Amides with 2H atoms instead of R groups, they have more hydrogen bonding, similar to the case with the amines we saw earlier. And so they have higher melting points or boiling points than those with only one or no H's at all. And what's interesting is that amides actually have higher boiling points and melting points than all other classes of molecules because of their hydrogen bonding capabilities. They have hydrogen bonding capability basically here, and in these regions over here as well. So they can do a lot of hydrogen bonding, even though it's not like the powerful OH hydrogen bonding, they have a lot, and that makes up for it. Amines are not that powerful. They don't have as much hydrogen. They have weak and not as many hydrogen bonding sites. Amides, they have the NH, but also more sites here as well. So a lot more potential for hydrogen bonding, which is why if you have an amide with a lot of H here, then you're likely to have a higher boiling point than an equivalent carboxylic acid, for example. And then before we conclude, remember to look over the priority. Amides are pretty high in priority. They're higher than most things except for esters and carboxylic acids. And in later videos, you're going to see some examples of more complex cases where you have multiple functional groups, and you'll need to come back to this priority list here. We've already seen some example where you have a hydroxyl with amides, for example, and that is just a stepping stone to knowing how to do more complex examples later on.